Okay. So section 5.2, we've been talking about solving trig equations. So let's just kind of continue looking at some examples. So we're going to be, these examples we're going to be solving for x on the interval from 0 to 2 pi. Notice that 0 has the bracket and 2 pi has a parenthesis. So that means 0 could be a feasible answer, but 2 pi could not be, right? All right. So looking at our first example here, what do you guys think we should do first to solve this? Cosine squared 3x equals 1/2. Blake?
Okay. Can we split up the cosine squared?
Well, if it doesn't equal 0, that's probably not going to be terribly helpful.
Oh, okay. Yep.
Right? If it was equal to 0, then sure, you could use the zero product property on that kind of thing. But here, where it's equal to 1/2, Luke? Square root both sides? Yeah, let's do that. That's going to be an effective tool to get rid of the squared. Now, when I square root both sides, what do I have to remember? Plus or minus. Okay, when I square root 1/2, the square root of 1 is 1. And then I have square root 2 in the denominator. When I rationalize that denominator, I'm going to end up with root 2 over 2. I'm just going to kind of explain that aloud rather than writing down the steps for that. I hope we're okay with that. Okay. Since this is a plus or minus, I'm going to break this off into two equations. One where cosine 3x is equal to positive root 2 over 2. And one where it's equal to negative root 2 over 2. So far, so good. Then what? No, because we have to get rid of the cosines first.
You basically find the angle measures that are associated with those.
Yeah, so we'll do the cosine inverse to both sides. Everybody okay there? So to do that, I'm going to go to the unit circle and look up where the x-coordinate is root 2 over 2. That happens at pi over 4 and also at 7 pi over 4. But remember, since the coefficient on my variable is not 1, I'm going to write these like my infinite answers. And we'll do the same thing in the other one. Except here we're looking up at the unit circle where the x is negative root 2 over 2. That happens at 3 pi over 4. And then again at 5 pi over 4. Is everybody okay to hear? Yes, Paul?
What's that plus 2 pi k log k?
Right. So if I'm just solving this kind of a equation over no interval, that has infinitely many solutions, right? So what the way we write these infinitely many solutions is with this notation. So that's saying my solution is pi over 4 plus anything that's coterminal to that,
Oh, okay.
right? Because plus 2 pi k is any multiple of 2 pi added or subtracted to pi over 4. So just saying,
So what's the K?
so the k is my factor, where k is an integer.
Okay.
So like 2 times 2 pi or 5 times 2 pi or negative 7 times 2 pi. Those are all going to give me some stuff that's coterminal because the integers are positive and negative whole numbers. Okay? And I need to do that anytime the coefficient on my x isn't 1. Okay. Is that catch everybody up to where we're at here? Next step would be to divide by 3. So the thing we have to be careful about here is that we're dividing both the angle measure by 3, but also the 2 pi k by 3. That gives me pi over 12 plus 2/3 pi k, where k is an integer. It's going to be 7/12 plus 2/3 pi k, where k is an integer. Now I acknowledge that 3 pi over 4 divided by 3 can be reduced, but I'm going to write it as 3 pi over 12 still. I'm going to do all my reducing at the end, because I find it a little bit computationally easier to not have like a bunch of different denominators rolling around on this if I don't need to. So I'll just worry about all my reducing at the very end. Of course, you're perfectly reasonable to reduce along the way if you want to. I don't. Everybody so far so good to here. Okay, remember the interval that we're solving over is 0 to 2 pi. So what I'm going to do is I'm going to use these infinite solutions that I've created to generate all the solutions that land inside of that interval. So if I look at the first solution set, pi over 2, and if I minus 2/3 of a pi, that's going to give me a negative value, right? That's not inside of the interval that I need. So I'm going to ignore all of those for each of these, because any of these angles minus 2/3 pi is going to be a negative number. So I'm only going to worry about adding. FYI, 2/3 is the same thing as 8/12 when I make a common denominator there. So my first answer here is going to be pi over 12. Plus 8/12 is going to be 9 pi over 12. That's still less than 2 pi. And then next one is 17 pi over 12, still less than 2 pi. And then 25 pi over 12, ooh, that's too big. So that one's out. So we found all of the solutions from the first answer. Now we'll move to the next one. So 7 pi over 12 plus 8 pi gives me 15 pi over 12. That's still good. That's less than 2 pi. Add another 8/12 gives me 23 pi over 12. That one's still good. The next one would be 31 pi over 12. Oh, that's too big. It's doing okay. All right, we'll go to the next set here. So 3 pi over 12, If I add 8/12 to that, I get 11 pi over 12, still less than 2 pi. Another 8/12 gives me 19 pi over 12, still less than 2 pi. Add another 8/12 is 27 pi over 12, and that's too big. So we have 5 pi over 12, and then 13 pi over 12, 21 pi over 12, and then 29 pi over 12, and that's too big. So those are going to be my 9 solutions to this. Worth pointing out here that we have a couple that could reduce there. If I'm going to write my final answer, like in an answer key or whatever, I'm going to make sure that those are reduced. Not the end of the world if you didn't reduce it on your assignment, but if you were to check it, surely I would have reduced answers in a key or whatever. Ooh, Billy, that was a lot. Do they always get this bad? Well, they don't always, but they certainly can be that bad. That's not even necessarily as bad as it could get. Not that I have any on this particular assignment that are much worse than that, but there's no reason it couldn't be much worse than that. Yeah, you're welcome, guys. Let's do another example. Oops. So let's say we have this, tan 2x times sine squared of 1/2 x equals tan 2x. What should we do first for this? Good. What do you definitely not want to do here? That is very tempting. Divide both sides by tan 2x. Very tempting to do. Very bad to do that. Why is it not okay to do that? Well, it would enormously simplify the problem if we're able to do that. Why would we? What's bad about doing that, though? Well, tan 2x has a variable in it, right? Everybody agree? So conceivably, tan 2x could equal 0, right? And if you're dividing by 0, that is very bad.
But why can't you just say that tan 2x is not equal to 0?
Well, let's see what happens if we actually try to solve this. So we get to this spot, you'd factor off the tan 2x, right? Everybody agree? Then what's up?
No, you're right, sorry.
And then you'd apply the zero product property. And what does tan 2x equal? Expressly is equal to 0. So there's not a way that you can get around just pretend tan 2x doesn't equal 0. Well, the solutions are exactly when tan 2x is going to equal 0.
Well, okay, but wouldn't it be 1 times tan of 2x? So if you divide it, wouldn't you still have 1 on the other side?
Sure, but you divide by 0. I can show you that 1 plus 1 is 3 if I'm allowed to divide by 0. I can show you all kinds of crazy things if that's okay. But this is the point of why we can't divide by tan 2x, is because we're expressly interested when tan 2x is 0. You would definitively be dividing by 0. You'll lose a whole mess of solutions doing that. And make your math teacher very, very sad. Okay. Is everybody, were we okay to how I got to here? Okay. So the first one, well, we'll just take tan inverse of both sides. The second equation over here, what? We're going to have to add 1 to both sides. Then we'll have to square root both sides. That gives us a plus or minus, so we have to split that. Right? And then we do the inverses to both sides of these. So far, so good? All right, I'm going to go back to the tangent equation. So we're going to go to the unit circle, and we're going to look for when y over x is equal to 0. Yes?
I was confused when you take the inverse of
If I have like sine x is equal to 2, well, let's say 1/2. If I do the sine inverse of both sides, these are inverses, so they necessarily cancel each other out.
Oh, okay, so that's why 1/2 stays on the other side.
Yeah,
Okay.
that's all we're doing.
Okay.
Just like if you divide both sides by 3 or took the square root of both sides or whatever, we're just using inverses to cancel. Cool? Okay, thank you. Oh, it says that you're supposed to keep this with you. No problem. All right. So tan inverse of 0, I'm going to go to the unit circle, look for the place where y over x is equal to 0. That's what tangent is. That's really the same as just wherever y is 0, right? So that happens expressly when the at 0 degrees and at, or I'm sorry, 0 radians and at pi radians. But again, these are, the coefficient on the x isn't 1. So I'm going to use the infinite solutions. Okay, let's go over to these ones. I'm going to go to the unit circle when y is 1. That happens at pi over 2. And the other one, we're going to go to the unit circle where y is negative 1. That happens at 3 pi over 2. So far, so good. Okay, let's go back to the tangent answer. I like to kind of do it all in one line because I'm the kind of idiot that gets done with one of these and is like, oh, okay, I'm all done, and forget to do the other one. That's the special kind of moron your teacher is, so that's why he's doing it this way that seems kind of convoluted to do like one step at a time for all 3 of them at the same time. You're free to work on it any way you like. So divide both sides by 2.
Wait, what is the range on this? 0 to 5?
Yes.
Wait, what happened to the negative 1 for the sign?
Still over there.
Oh.
Just off the screen. All right, so tangent, we have 0 plus pi k, and then pi over 2 plus pi k. But think about what those answers are saying. So for the first solution, we're getting stuff like 0 pi, 1 pi, 2 pi, 3 pi. The second solution, we're getting things like half a pi, 1.5 pies, 2.5 pies, 3.5 pies. You put it all together, and you're getting 0 pi, half pi, 1 pi, 1.5 pi, 2 pi, 2.5 pi, 3 pi, 3.5 pi. So really, what do we got here? I can combine these together and really just say this is 0 plus pi over 2k. And that makes life just a little bit easier to deal with. Again, we're solving this over 0 to 2 pi. So we have 0 pi over 2 pi, 3 pi over 2, 2 pi, but we don't really have 2 pi. Remember, our interval is bracket 0 to 2 pi parenthesis. So 2 pi is not actually a valid solution in our solution set, so we shouldn't include that one. So we have those 4 from the tangent side. Let's go back to the sine side here and finish this guy up. So we'll multiply both sides by 2. So that gives me pi plus 4 pi k. So that's going to be things like 1 pi, 5 pi, 9 pi. But all the answers there are already answers over there, aren't they? So I don't even need this solution. It's worthless. Doesn't tell me anything that I don't already have. I don't have to write solutions more than once. I can just ignore it. Everybody okay with that? Luke?
Why would 4 pi be a valid answer when our range is 0 to 2 pi?
Okay, so they're not valid answers, but those are the answers that infinite solution generates.
Okay.
So it's like 1 pi, 5 pi, 9 pi. All I care about is all of those answers are already answers over here. So because I've already done that one, I don't need to do pi plus 4 pi k.
In this problem, there's only 4 answers because only 4 answers fit the range.
4 answers so far. We still have one more piece to deal with, right? 4 answers so far. Let's see what happens here. So again, multiply both sides by 2. So here we're going to have things like 3 pi, 7 pi, 11 pi. All of these answers are still here. So those set of answers don't matter. Not that any of them would have been inside of the range anyways. But we've already counted anything we could have gotten out of there from the other one. So these 4 are our only 4. Boy, that's awfully frustrating, isn't it? When you go through and solve something, you don't even get any new solutions out of it. But sometimes that's just the way the cookie crumbles. And certainly if this was an infinite, if we asked to solve this over all real numbers, the only answer I would have reported was this in green, since all the other answers are redundant or could be combined into that one. You know what I mean? Which again, if you're just looking at the answer key, you're probably going, wait, what the heck? You really have to kind of think about what these answers are saying. And, oh, it's just, this answer includes that answer. Okay. Which is lovely, right? When you have like 2 things that are infinite, but one is a proper subset of the other. Like, wait, what? Isn't that awesome? Those are mind-bending mathematics for you. I get excited about that kind of stuff. I don't know where your head's at that you can't get excited about that. I think it's pretty rad. All right, let's do a couple more. So let's say and let's do something different. So this one we're going to solve from 2 pi to 6 pi. Whoa! Crazy town. Just FYI, as soon as I see that we're solving not over 0 to 2 pi, means that I'm going to be using the infinite solutions. So like, even though there's no coefficients on my x's, I'm still going to be using infinite solutions for this. FYI. All right, what should we do first here? 2 cosine squared x plus 3 cosine x minus 2 is equal to 0.
Gotta factor that bad boy.
Yeah, hopefully you recognize that looks awfully like a quadratic, right? So we're going to need to find two things that multiply to give the leading coefficient times the constant term and have to add to the linear coefficient. Multiplies to give us -4 and adds to give us +3. It's a brain buster there. 4 and -1, yeah. So remember, since the leading coefficient isn't 1, this doesn't take me straight to my answer. But it just describes to me how to break up that linear term. Everybody's okay, remembered in doing this? All right. I'll make my two groups. From the first group, I can take out a greatest common factor of 2 cosine x, and I'm left with cosine x plus 2, right? From the second group, I can take out a -1, very good. What am I left with? Cosine x plus 2. Notice each of those have a cosine x plus 2 in them. So if I factor that off, I'm left with 2 cosine x minus 1. Now we're all factored up. Cool with that? Zero product property, that bad mama jamma. So it allows me to take each of those factors and set them each equal to 0. Remember, we can only do this if they're equal to 0, right? If the factored form was equal to 1 or something, you're out of luck. It means FOIL that bad boy back out, subtract the 1 back over, and start over again. Ugh. I know. All right, so the first one, we will subtract 2 from both sides. Go ahead and do the cosine inverse. And notice that we're taking the cosine inverse of something that's smaller than -1 or bigger than +1. That's undefined. So there's no solution to that piece. That's great, right? That saves us a whole heap of work. So we're just dealing with the other equation then. So we'll add 1 and then divide by 2. Do the cosine inverse. go take a look at our unit circlet where x is equal to 1/2. That happens at pi over 3. And then also at 5 pi over 3. Remember here we're solving from 2 pi to 6 pi. So certainly pi over 3 is too small, right? I'm not even going to bother writing it down just to cross it out. Everybody's good with that? Way less than 2 pi. If I add 2 pi to that, I end up with 7 pi over 3. I do it again, I get 13 pi over 3. That's still less than 6 pi. I do it again, I get 19 pi over 3. That's too big. Doing the same thing down here. Clearly 5 pi over 3 is too small. That's less than 2 pi already to start with. I add 2 pi to that, I get 11 pi over 3. That's good. I add another 2 pi to that, I get 17 pi over 3. Still less than 6 pi. I add another 3 pi or 2 pi to that, and that is too big. So I have these 4 solutions. Everybody okay with that? Okay. What do you guys think about these solving guys? Probably need some practice, but overall, I don't think it's the trigonometry part. I don't think is terribly difficult. Sometimes the algebra pieces can get a little bit oopsie-daisy-ish. So from the book, problems 15 to 42 are the solving ones. Yeep. You know what's the worst part about this? Is they're all A, B, C, D problems. But here's the good part. A is solving from 0 to 2 pi. B is all real number solving. So what do you have to do between the two answers? You just put the plus 2 pi k onto the end, right? Part C and D is just then, okay, over some weird interval. You've already got the infinite answer, so you just need to like use the infinite answer to generate the stuff in the intervals that you're solving over. So it's a little bit not as bad as maybe it looks, but it's still kind of bad. I'm not gonna lie, I'm not sugarcoat it for you. Like there's an upside to it in that like all your answers for A, B, C, and D are not like do the problem over again answers. It's just like, okay, and then extend it a little bit more. Okay, and then extend it a little bit more. So like everything you had done before that still is good, helpful. But it is 4 things. It's still 4 things to do for every one of those. There's kind of a lot of them written there. I acknowledge this. Okay. We are going to also talk about 5.3 today. We're not going to do anything on Thursday. It'll just be like a general work day. And something else might be happening Thursday that happens for every chapter, you know. But if you're thinking about that thing that happens in every chapter that hasn't happened yet for this chapter that could happen on Thursday, and we've really only talked about how many sections? How many have we asked questions about the homework regarding? 1, just 5-1, right? That's the only section that you've had a chance to ask any homework questions about. So what would the homework quiz potentially be about? 5-1. So just think if that were to happen, hypothetically, that was the homework set 1 to 14, yes. Oh, you will not have to memorize the identities for this chapter's test. After this test, I'd expect you to know the basic identities in the future, but for this chapter, no, I don't expect you to have them like instantaneously memorized. It's probably a realistic, right? Like the minute after you see them, I don't expect that. But after we've worked on them for a chapter, maybe then we're expecting you to know them. All right. Yeah.
Was 5-1 the trig identities?
Yes, we did the trig identities in 5-1. Simplifying, and then there was like, you know, if you use an identity to find the values for the other trig functions, if, you know, these things, right? There's like 2 different kinds of problems on there, basically. No worksheet yet. Okay. Proving identities. So these are my rules for you guys when solving your identities. So the first rule is you can pick which side you want to work on. You start out working on one side. You end when you get to the other side. You can't work on both sides and meet somewhere in the middle. Okay? My advice is typically start with the more complicated side. Rule number 3, when in doubt, convert everything to sines and cosines. Combine fractions by using common denominators. The difference of 2 squares factoring pattern is your friend. When deciding what identities to use, keep your eye on the prize. Think about what it is that you're trying to end up with and try to keep moving towards that rather than just anything you can do. Think about really what you should be doing. Okay? So we'll do a couple of examples of these, and then will be done for today. All right, so here we have the identity cosine x over 1 minus sine x equals 1 plus sine x over cosine x. Which side appears to be the more complicated side? I'd say they're about the same, right? If you want to work on the right-hand side, I'm happy to do that, though. Let's do that. Oh, so you think we usually want to start with the more complicated side. So if you say the more complicated side is the left, then we'll start on the left-hand side and try to end with the right-hand side. Here, I don't think it matters much one way or the other. Okay. So you want to start on the left-hand side then, right? I should say correct. Usually you don't want to say, turn left now, right? That's a really confusing way of giving directions. Okay. Good. So we're going to start on the left-hand side. Fine. What do you want to do first? But it's not sine squared. Let's make it that then. How are we going to do that?
Multiply by sine over sine.
Close. Read rule number 5 again.
Number 5.
Rule number 5.
Oh,
wait.
I don't take
Combine. Oh, wait, no.
Oh.
It was
It's your friend. Oh.
What should I multiply the top and bottom of this fraction by? Tegan.
1 plus sine.
Yeah. So that's going to get us exactly what Anise was hoping to get. Actually, I'm just going to write it this way. Why won't I bother to multiply this out? Why am I declining to do that?
Want that those sides to stay there instead of distributed.
Eye on the prize, right? I want that 1 plus sine in there. The only way that cosine's going away is if it gets reduced out of there. Better, might as well keep it in factored form rather than having to multiply it out and then factor it back off later. Bless you. Okay. So we're here. Everybody okay?
Yeah.
Now what? Anise.
Oh, okay. Is that a cosine before?
Mm-hmm.
Okay. Can you scroll forward?
I called on you because this was your idea initially, right? So Anise said that if we use the first Pythagorean, if I had like subtracted sine squared from both sides,
It's going to be cosine squared x. You're going to replace that.
I can say that cosine squared x is 1 minus sine squared x. That's what you were trying to do initially.
Yeah.
That's why I called on you right now, because it was time to do it.
I actually forgot.
Oh, that's okay. I wasn't calling on you to like be a jerk. I was calling on you because I thought you had the right answer. Is that okay
Yeah.
with everybody? Then what?
Cancel out the cosine.
Yeah, we just reduce. And now they're the same, right? Notice how I'm working this problem where I'm kind of working vertically down my sheet of paper. This is how I'd like you to do it as well on your pieces of paper. Probably pretty crummy of me to tell you that now after you've probably been doing whatever you wanted. But it makes it much easier to assign partial credit when you're working kind of vertically down the page and I can clearly see your line of thought. Okay, let's do another. Flip my page here. All right. Which side would you want to start working on? The left certainly seems a lot more complicated. That's not too much of a stretch there. Okay. What should we do first then? Yeah, let's go ahead and FOIL the top out, or you could use your difference of two squares multiplication pattern. Tegan.
I would then change the top to sine squared.
Yeah, so using a similar reasoning that we did over here, you could subtract the cosine squared over to get kind of the same relationship Tegan's claiming to use. That works for me. And then that's tangent squared. And we're done. Nice. Okay. That wasn't bad, Mr. Kulik. Some of them you'll look at and you'll be like, okay, like I see what to do. And some of them you'll look at and you'll go, I have no flipping idea what to do.
Really good one.
This is a good one right here. All right. Which side do you want to work on?
Let's do the right.
Yeah.
Okay. All right. If you say so, I would pick the left, but we can work on the right. Let's do it. Okay. After this, I'll show you the way that I would have done it, using the left side.
Can we factor out the side squared x, or is that not possible?
Sure, you can factor out a sine squared. That's a good idea.
I think there's more identities.
Yeah. What's up, Luke?
Broke up the sign board into sign squared. Can you do that?
You want to do it into sine squared times sine squared?
Yeah.
I mean, you can. That's not wrong to do that. I would suggest doing something different.
Well, I don't know what you would do with the 1 minus 2 sign squared. I'm not doing that too.
Look at that as one whole thing. What does that look like?
Oh.
That I've underlined in green. What does this look like?
Yeah.
Looks like a quadratic that you could factor, right?
Oh.
Let's see what happens when we do that. So we need to multiply to give us 1 and add to give us -2. -1 and -1, right? Okay. No. Multiply to give us +1 and add to give us negative. Oh, yeah. -1 and -1, right? Okay. So we have sine squared x minus 1 times sine squared x minus 1 times cosine. Everybody agree with that? Why is it sine squareds there instead of sine?
Oh, is the sign just 4?
Yeah,
Sign is 4.
right, because it's not quadratic, it's in the quadratic form. So we have to make sure we adjust the exponents accordingly. Okay, now what?
Then you turn the cosine.
No, those don't turn into cosine squareds.
Why not?
Well, because it's sine squared plus cosine squared equals 1. So cosine squared x is equal to 1 minus sine squared, not sine squared minus 1.
Could it be a negative cosine?
Oh, so you want to do that?
I don't know.
That's okay. You can do that.
We'll go faster than that.
Yeah, for sure. That's a perfectly valid thing to do. Everybody agree with what Luke suggested there? Arya?
Do you turn it into 1 minus cosine
One minus what?
Like, isn't sine squared x the same as 1 minus
Mm-hmm.
cosine squared x? And then just 1
Right, that's the same. That's essentially the same thing Luke did when he saying multiply by -1. Same idea, right? Same result. But yeah, we can do that. Multiplying both sides by -1 gets you what you need. The way I would have thought about it is I would have factored a -1 out of each of these to switch the signs around the way I wanted to, but you can do it that way. The way you've described is not incorrect. Let's do it your way.
Then you just multiply all the cosines, that cancels the negative, the cosine of the sine squared.
Yeah. And you're done.
Wait, can you explain the stuff that we did?
Yeah. So were you okay with how we got to there? By just subtracting the signs from both sides?
Yeah.
All Luke did is he multiplied both sides by -1.
Oh.
He said it in a weird way, but I knew what he meant. And I wrote it in a way that was like super, should have been like really, oh, okay, sure, of course you can do that. Like Luke said, we'll just make it negative cosine squared. And it's like, okay, I know what you mean
I
there.
don't know how to express it.
Yeah, no, it's a totally, like, you and I were having a conversation, I understood, so we're good. I reworded it in a way that would, like, feel like it didn't fall out of like Luke's brain and just like, oh yeah, Mr. Kulik said that was right. I have no idea why. You know? But that's probably the process that was going on internally.
Yeah.
That like you just couldn't verbalize well.
Here's the term.
Yeah. Yeah.
They were turning.
Okay.
They were going an overdrive, in fact.
So if you had chosen instead to do the other side, here's what I would have worked on the other side, because I would have said, okay, well, I know I have to get that cosine separated, so I would have just done that. Just turn cosine to the fifth into cosine to the fourth times cosine to the first. And then said, okay, well, cosine to the fourth is cosine squared squared, because I know that to get sines, that cosine to the fourth has to somehow turn into all this mumbo jumbo. The only way that's going to happen is to get it into terms of sines and ones, so the Pythagorean's my only option there. Right?
So much easier.
And then
Literally, it's just
I just expand that out. And then I distribute the sine squared through. And there I'm at it. That's what I probably would have done, just because it felt like there was less guessing as to what to do to me. But like either in general, like you can work on either side. Like the problem is doable either way. Like you could have even gone back to this silly one. You could have started with the tangent squared side. It's possible to get to the other side. You have to be a little bit clever to do that. I would never suggest doing that for us, but like you can absolutely do it. You'll probably have to do like a +1 -1 thing at some point to do, you know, to generate what you need. But, you know, it's okay. It's okay. We'll stop here.